Otherwise, starts a new thing. Yeah.
Okay, so let me see whether this is coming up.
Yeah, it's working. Starts a new thing. Yeah.
Yep. So it works. It works really well already. Okay, so let's still wait for a few more minutes.
Sounds good.
So that we can test everything. Yeah, we can see the slides fairly well.
Right. So let me try to
we
find
can hear well. Yeah.
Chat window. Okay.
Try to say something maybe.
Oh, so for me?
Yeah.
Just to test the audio?
Yeah. Yeah.
Okay. So how about this?
It looks okay. Yeah, yeah. It looks okay. There's, I mean, I don't know whether it's the mic that is just touching on your hoodie.
Yeah, it's possible. So there was some kind of noise, right?
Just you know, very marginal noise.
How about
Try now?
How
that's
about
perfect.
this?
Yeah.
Okay.
Yeah, that's
great.
perfect. Perfect. Yeah. So this is absolutely great, and I believe we can just a few more minutes.
Mm-hmm.
Okay, I guess we can get started. So let me just start the recording. Are you all right, Gang? So good.
Yes.
Yeah.
Yes,
okay. Let me just welcome everyone again, to our another session of our privacy and security in machine learning seminar series. Today, I'm really pleased to have Gang here. So we are friends, collaborators. So we've known for a little while, and I'm really looking forward to listen to what Gang has to say about combating online deception in the age of machine learning. And Gang is an assistant professor at UIUC, obtained a PhD at UC Santa Barbara, a place that also I know because I spent a couple of years as a postdoc there. So very lovely place. Then a bachelor from Tsinghua University. And then he also had some academic experience at Virginia Tech before joining UIUC. And his research revolves around security and privacy, data mining and intermeasurement. The work has been published in top-tier conferences. He sits very often in the program committee of top-tier conferences. The recipient of the NSF Career Award, Amazon Research Award, Google Faculty Research Award, and a series of other best paper awards, including ACM CCS and Sigmetrics. So I'm really happy to have you here. Thanks for accepting our invitation, despite the early call for you? Like, what better way to start a day, with an interesting talk. So the stage is all yours, and please take it away. Thanks.
All right, thank you so much for the introduction, Lorenzo. Hello, everybody. I'm Gong from University of Illinois. Today, I'm very happy to be here to talk about our recent work on online deception and machine learning. All right, so if we look at some recent events, they seem to suggest that human factors are still a weak link in security. So for example, in 2020, Twitter had a major attack that compromised many high-profile user accounts. This includes the accounts from Joe Biden, Bill Gates, Elon Musk, and many others. Now, these accounts then sent out tweets that try to collect Bitcoin from internet users. Now, it turns out that this is an attack done by a group of teenagers who did social engineering against the Twitter employees and tricked them to give away internal access. So human factors as a generic weakness can also be exploited in other ways, such as disinformation campaigns that aim to manipulate public opinions. For instance, during the current Russian invasion of Ukraine, there are many campaigns trying to push false narratives about the reasons for invasion and stories around civilian casualties. Facebook and Twitter already took down several of these networks, and their investigation also shows some interesting results. It turns out that many of these networks try to create fake personas that aim to impersonate news reporters and military personnel to gain people's trust, and they even use AI algorithms to generate some of their photos and content. So if we take a step back and look at the landscape, the trade-offs in online deception campaigns, you can see there's a tension between the scale of the attack and the quality of deception. For instance, the traditional spam and phishing campaigns, they usually comes with a larger volume, but a low quality content because the contents are usually generated by text templates, therefore they share a high similarity. On the other extreme, we have spear phishing attacks, which are usually small scale, targeting a few persons or just one person. And the content is highly specially customized so that it is specifically working for that person. So therefore, they are usually of a high quality. So somewhere in the middle, we have those propaganda-based campaigns that were basically use human agents that to craft those news articles and media content, so they're of high quality, but also because the need for human workers, so they are operated at a small to medium scale. So the question here is that, are there attacks that will break this diagonal line of trade-off? So are there something on the top right corner that are considered scalable yet high quality deceptions? So in recent years, we started to see some movements from the attackers to that direction, mostly driven by the development and advancement of machine learning algorithms. So more specifically, today's machine learning algorithms have significantly improved our ability to manipulate and even synthesize media content, broadly including images, videos, text, and voices. So for example, you can very easily swap a person's face in an image or video to spoof their identities today. You can even create a face that do not exist in the world by purely synthesizing using models. Text-based models such as GPT-3 can do a really good job generating convincing content to human readers. And you can even clone people's voices as a way to impersonate their identity. So these capabilities collectively make it as a possibility to scale up some of these deception campaigns. So this is not just a theoretically possible concern, but we start to see some anecdotes in practice. So not too long ago, so a CEO of a UK energy firm was scammed by someone using deep fake voices to impersonate his supervisor or boss, and convinced him to transfer more than 200,000 euros to the scammers. In a separate event, people found deepfake generated social media profiles on LinkedIn that have successfully connected with people in the high political circles in the Washington, D.C. areas. So if you look at this Kitty Jones person and zoom in her profile photo, you can clearly see some algorithm-generated artifacts that indicates that this is not an authentic image. So based on this trend, we wanted to ask some basic questions. So the first question is, how is machine learning used and or can be used in different type of online deception attacks? How do users perceive or react to algorithm-generated fakes? And then finally, how to build effective defenses that can help users. So my research takes a data-driven approach, try to find answers to these questions. So as a general approach, my first step is usually to use measurements to understand how the attack works by collecting and analyzing real-world data. And then I like to work on behavioral models to capture the behavior of attackers and legitimate users. And then based on the insights from the measurements and the modeling, I'm looking to build practical systems as a security solution and use measurements in a user study to assess their effectiveness. In this talk, I will pick 2 examples within this framework to discuss some of the recent findings. So in the first part of the talk, I will talk about how machine learning can pose a threat to our existing tools to study online deception. So I will use perceptual hashing as an example, as is commonly used for media content forensics and a reverse content search. Then I will switch to look at the user perspective to study how users perceive and establish trust towards algorithm-generated fakes in a social engineering context. So the reason we're interested in perceptual hashing is because it is commonly used for cybercrime analysis, forensics, such as detecting phishing web pages or identifying fake profiles in social media. What it does essentially is generate a small hash code or fingerprints for images, such that similar looking images would have similar hash code. For example, in this image of a little girl, it has a 64-bit hash code. And if you add a small red border to this image, so this image is still visually look very similar, it will end up with a very similar hash code with a small Hamming distance. So Hamming distance measures the bit difference between 2 hash strings. So as you can see, the distance is only 4 out of 64. But if you look at a very different image, so the Hamming distance can go as far here as 30 out of 64, indicates that the image has been visually different. So because of the ability to measure similarity of images, so perceptual hashing can be used to build reverse image search. People use reverse image search to find a similar looking content. So for example, when people are, let's see, browsing a Tinder profile, there's a profile of interest, but you want to check if this photo is authentic. One way people can do very commonly is to send this image to reverse image search engines such as Google and T9, and look at how this image was used in other contexts and how they were indexed on different websites. Now, based on the search results, it's usually easy to find evidences that this particular photo, as in this example, look like a model in a stock image that has been used by very different contexts, and people even report that this image has been used by fake profiles. Very similarly, you can reverse image search for images spread in disinformation campaigns and try to find their sources. For example, in this image, it shows two people. One on the left is activist Lena Sosa, and the right person is Stacey Abrams, who was the Georgia governor candidate at that time. So they were in a campaign events together. So that's the original version of the image. So a few months after that campaign event, somebody on the internet manipulated the image by adding a few keywords to the campaign sign. If you can see clearly, they are communist and the Muslim Brotherhood. Now, this new image got a viral on the internet, especially on Twitter. But if you have your suspicion and you do a reverse image search, and you could find the original image and the source and try to understand the context better to make informed opinion. So this tool has been used quite often by journalists to do fact checking. This is especially true during the current, Russia invasion, where numerous images about military combat, civilian casualty events, they were spread online. But if you search on some of the images like this, people say that they are often taken out of context from past events many years ago. You can even find the original image that way. The question is, how reliable is this perceptual hashing-based reverse image search? What if the attacker can do more by, for example, adding some noise to the image and make sure that when people search it, they cannot find the original source anymore? So in this case, you find a related image, but really doesn't tell you much about the original image of interest. So here in this project, we try to explore this type of attack and try to understand the robustness of these algorithms. So the general threat model is very simple. So from the attacker perspective, given a particular image, they want to generate an attack image that look very similar, but have a very different perceptual hash code. So the consequences is that when people search this attack image, they can no longer find the original source. So the secondary goal of the attacker is that they need to work under a black box model because real-world search engines do not reveal their implementation details. And also, we should expect there's some basic defenses out there for real-world search engines. So how to do that? So if you look at the standard perceptual hashing algorithms, they work in a way that is really kind of, predetermined in a sense, right? So given an image as input, so you first reduce the size and to reduce the computational overhead, and also convert the image from a colored version to a grayscale version, again, for feature extraction. And then you can apply discrete cosine transformation to extract features from the frequency domain, and then reduce this DCT matrix to a smaller size and compute a median value. Now, the hash code can be easily generated by comparing each cell in this 8x8 matrix to this median value. You get a 64-bit hash code. But if you look at this perceptual hashing generation algorithm, so it's not a very differentiable, meaning that you cannot directly run a gradient descent, for example, to generate noises. So we needed to pivot a little bit to use a function to approximate this p-hash process. So we started with a very simple loss function. The goal is to learn attack image, again, as you can see, XA, such that you minimize the visual differences with the original, but causing a large distance in the hash function space. So the first loss term is a look at visual differences. And in the past, people have used things like L2 distance, structural similarity index measure. But we found that the more effective one is called LPIPs, which is a more recent metrics defined by a learning-based algorithm that has proved to work better to capture human perception. This has been validated by other researchers in user studies. So we pick LPIPs. And in terms of the hash code space, so in order to make it differentiable, we simply use a hinge loss function to measure the Hamming distance between the attack image and the original image, normalized by a distance threshold defined by the attacker. So here, if the attacker wants to cause a 20 bits difference in a 64-bit hash code, then the targeted DT needs to be 20 out of 64, which is 0.31. So with this setup, we can run a zeroth order optimization to estimate the gradients and compute the perturbation. The problem with this basic design is that it's very slow because of the optimization process. So to speed things up, we introduce a grayscale initialization step. So the idea here is that given this RGB image, we first convert it into a grayscale and learn the noise directly on this grayscale image. Then we can use the noise to apply them directly to the RGB channel and run another several rounds of optimization on these channels to generate the color version of the image. Now, this process gives you about 10x speed up because it dramatically reduced the search space. And also the reason why it works well is that the perceptual hashing algorithm already calculates their hash code based on grayscale images. So this grayscale initialization get the algorithm to have a very good starting point or initialization values. So as a kind of a final step, as we expect that real-world search engines may have some sort of defense, we don't know what they are, but we just try to play with a few ideas how to make this attack image more robust. So one of the idea is to do attack over an input ensemble. So the idea here is that you want to make the attack image not only different from the original image, but also different from the slightly transformed version of the original image, again, in the hash code space. So we use slightly different transformations that do not change too much of the perception of those images. So another idea is called attack over input transformation. So this time you tweak the loss function a little bit differently by let the slightly transform the image as the comparison baseline. So the idea here is that you kind of first transform the image and then try to push the attack image even further away to enlarge the robustness. So here now we can have this idea. So we wanted to kind of evaluate the attack a little bit in a controlled environment first. Now, to do that, we need to build our own kind of controlled search engine to validate some trade-offs. So we built a backend database here using ImageNet and face data set of 1.28 million images. And those images are indexed in the backend database using their perceptual hash code. And then what you can do now is to search images using queries, and then as a kind of mimic the reverse image search. And the database will return similar looking images based on distance threshold. So here, in order to control the false positives, so the threshold tau needs to be relatively conservative at the 0.2 level. So to evaluate the performance of the search in general and the attack effectiveness, we look things like false positive rates, which shows the average number of returned irrelevant images from the image queries. The top key hit rates measures the percent of the images that their true matching results are among the top key return results. And field query rates measures the likelihood of not returning the true matching images. So if you look at the basic attack right here, so we define the target hash distance of the attacker to be 0.31, which is comfortably bigger than the p-hash searching threshold, which is 0.2. So after the attack optimization, we can see on an average, either the ImageNet or face data set can get closer to this desired distance. And the perceptual differences measured by the LPIPS value is around 0.3, 0.5. They're all below 0.03, 0.05, which is below 0.1. This is a kind of acceptable range. So the attack impact is very clear. As you can see here, they are reducing the top 5 hit rates and increase the field query rate. So for ImageNet, for example, the top 5 hit rates is 0%, and field query rate is 100%. Means that the true matching image now do not return because of the attack. So we also try to move the evaluation to the real world setting, where we experimenting with real world reverse image search engines such as T9, Google, Yandex, and Microsoft Bing. So the additional challenge to do real world experiments is that now the search engine will often index the image in multiple versions and slightly change the versions. Because one image may be used by different websites under different contexts. They might also have slightly different version of it. So we need to manually examine those search results in order to calculate false positives and false negatives. So here is an example, right? So if you search this original image and the search engine returns several results. So the hope is that when you search the attack image, the search results, the true matching results are dramatically reduced or even to 0. So here is the experimental results. We take a strong attack from our control experiments, and then we run a test on these 4 search engines. So again, this is in a transferred setting where the attack is optimized in a control setting, and then tested on a black box, real world search engines. So I use a T9 as an example to show how to interpret the results, right? So the average reduction rate measure the average rates of reduce the search results because the attack images. So in T9, so 100% of reduction rates means that the return results are eliminated by the attack image. So therefore, the top 1 and top 10 hit rates are all dropped to 0%. This is a fairly successful attack. Similar results can be observed in Microsoft Bing, where the top 1 and top 10 hit results are also reduced to 0%. So Google is among the more resilient search engines. As you can see, the average reduction rate is 88%, and then top 10 hit rates is reduced from 96% to 36%. So this means is that about 64% of the search images, you can successfully eliminate their first page results to not contain any true matching images. So that's kind of still a moderately successful attack. So for Yandex, we found a very different attack impact. So as you can see, the average reduction rate is a negative value, meaning that it actually introduced more results in the return results. But as you can see, that of the majority of the search results, 90% of them are false positives. They do not return relevant images. So overall, the attack was fairly successful. Now, we have thought about some defense ideas. So for example, on the server side, the immediate thought was, how about we put together a ensemble of different perceptual hashing algorithm and make joint decisions using their, hopefully using their diversity. The problem is that we further investigated an adaptive attack that jointly optimizes the noises for all those algorithms, and it showed that this still works well. And so this the server-side idea definitely need more work to really kind of robustify it. On the user side, we think the idea is more promising because imagine that we can develop a browser extension that would pre-process images using randomized transformations before running search. We can do this for multiple pre-processing steps for a single image, for a single user. The advantage is that every user would do this kind of pre-processing differently, across the board. So it is difficult for the attacker to pre-compute one attack image that is likely to work for all users. So this kind of a power imbalance between the crowd of internet users and the single attacker may give a hope to get some advantages for the defenders. So we're still in the process of exploring this idea to show if there's a good trade-off between usability and robustness. All right, so far we showed that machine learning can pose a threat to our tools used to investigate online deception. Next, I wanted to introduce a more recent study where we try to see how machine learning content was perceived by users, especially in a social engineering context. So the reason we started this study is that we start to see some attackers are starting to use the content created by deepfake algorithms in their campaigns, right? So we want to understand whether a user can distinguish those deepfake generated profiles from real ones, and what type of fakes are user good or bad at detecting, and whether user training or intervention can be effective to prepare them for these type of deceptions. So we start with a kind of a user study on LinkedIn platform. The reason we consider LinkedIn is because the LinkedIn profile has been used in real-world campaigns for social engineering, and also as a professional network, people it's kind of expecting unsolicited connection requests from people they don't know in person, for example, coworkers in the same company they didn't meet before, or headhunters or recruiters. So as you can see here, the profile contains several common attributes, and many of them can be generated by deepfake algorithms. So this includes photo. So we generate photos using StyleGAN2, which can synthesize images of human faces. And for names, we can simply sample from popular names in English, for example, and we specifically use gender-neutral names to avoid major conflicts with their photos. And then for this, bio summary, so it's a free-formed text, so we can use text generation models using GPT-2. But here, we need to kind of fine-tune the model a little bit so that the model can generate those kind of bio information type of text. So we fine-tune the model using a resume data set where it contains a large collection of this type of self-introduction. For the experience and education histories, they are essentially itemized, structured content. So this is much easier to generate by sampling those items from our resume data set. So with this tool to generate deepfake profiles, and what we did is to set up a scenario to do user study, right? So we design the scenario as a company merger where people might have the opportunity to interact with different roles such as human resource, IT experts, and billing managers. And we create profiles for all of them. And each participant would examine 3 random profiles and rate the trust level and decide whether they would accept or reject their connection request and explain their decision-making process. So in this study, we control 2 different conditions. The first condition is the different artifacts in the profiles. As we know that deep learning algorithms are not perfect, and often cases they generate artifacts in both images and text. So we try to understand if people can rely on such artifacts to help their decision making. So here, as you can see on the screen, we have one consistent profile condition that do not contain major artifacts. And then we have 4 additional artifact condition that is generated by changing specific fields or across fields inconsistencies. So for example, condition 2 consider the artifacts within the profile images. So here we specifically select images with highly visible artifacts generated by the StyleGAN2 model. And this is sort of to emulate the best case scenarios for users and also the worst case scenarios for attackers. And then for condition 3, it looks like a cross-field information between the profile image and their working experience, right? So we intentionally pick profile images of a younger age in their early 20s or teenagers, and then present the profile with 20, 30 years of working experiences in a particular industry or field. So we want to see if this kind of age inconsistencies cause suspicions to users. And then the 4th condition is about a text. Again, text generation models would have artifacts. So for instance, grammar errors or incohesive sentences. So here in this example, as you can see, the word versatile has been used multiple times. And then the last sentence is also a little bit strange when it says currently working part-time and then full-time and part-time. There's some kind of incohesiveness in those kind of sentences. And finally, for condition 5, this is an interfield looking at text inconsistencies between their bioinformation and their working history on the item list. So basically, things like incorrectly reference a company name that you didn't work at or a school name that you didn't attend, right? So the second condition we want to look at is user prompting, which is to understand the impact of potential intervention strategies. So the first group of users enter the user study without any prompting or warnings about any deepfake profiles. So they are instructed to basically examine the profile without any context. The second group of participants have a soft prompting. So in the beginning of the study, we warned that some of the profile might be fake, but we did not provide any concrete examples to explain what the fakes or deepfakes would look like. And the third group of participants have a more detailed tutorial. It's a hard prompt. We show what deepfake profiles look like and what the artifacts might look like, giving examples and show them how to detect them. So this is a sort of mimic user training. So in total, we collect valid responses from 286 participants recruited from Amazon Mechanical Turk. So we don't have time to discuss all the findings, but here are some high-level takeaways. So this figure shows a descriptive stats for one of the key questions regarding whether they would accept the connection request from the profile. So the x-axis shows the artifact condition, and the y-axis shows the acceptance rate. If you look at the leftmost bars, they are representing the consistent profiles. So not very surprisingly, people have a high acceptance rate, over 80% on these consistent profiles. But if you look at the red bar across the different conditions, these are these are the acceptance rate under the no prompting condition. Means that when people are not warned, even if they are examining deepfake profiles, the acceptance rate is still pretty high, 79 to 90%. So even again, when they're examining deepfake profiles with artifacts. The good news is that when you start to implement this prompting, so we can see that there's some drop in terms of acceptance rate across the deepfake profile conditions. and especially for the hard prompt condition under intra-image profile. However, if you look at the acceptance rate, it's still kind of high for 43% acceptance rate under the best case scenarios. So far, that's kind of just the descriptive stats. And we also ran statistical analysis to measure the significance of those impacts. So for example, we found that all the artifacts conditions significantly decrease the trust level and acceptance rate of deepfake profiles. And also the prompting can significantly decrease the trust and acceptance level of deepfake profile as well. So it shows that user intervention might be effective. And we also do not find significant difference between soft and hard prompts. This is probably a good news, meaning that maybe dedicated user training is not necessary. All we need to do is to warn them. But this is not the complete picture, right? So we also further analyze the open-ended questions to understand how users make decisions. So we found several, high-level findings. So for example, people found certain artifacts that are easy to detect, but some others are harder. So for example, artifacts in the profile images are easy to attribute to deepfake profile because there's no other alternative explanations other than this is fake. However, for some other inconsistencies, people have a hard time to attribute them correctly. So for example, many participants comment on that they found some grammar and sentence issues in their text writing, but they thought that was the profile owner who have bad communication skills or writing skills. It just, natural that people didn't write well. And they also very tolerant on age inconsistencies because they thought it's kind of common for people to use younger photos of themselves in on LinkedIn. So also we found that prompting has caused some undesired behaviors. So in some cases, participants start to identify non-existing artifacts and use that to determine fake profiles, the essentially false positives. And the more concerning issue is that people are more likely to use stereotypes to make decisions after heavy prompting. So for instance, there's a profile pictured a Black woman and her name is Chris. And participants comments that Chris is usually a white man's name. So they use this reason to determine this profile is a fake, even though that profile is illegitimate. So overall, we found that the both trained and untrained users are ineffective when they are examining the profiles of themselves. And even after hard prompting for the highly visible artifacts, there's still a 43% acceptance rate for the best case scenarios. So the takeaway is that individual users alone should not be the front line of defense, and we need more systematic defenses on those deepfake content before they can reach users. Also, it shows that prompting helps, but it may result in unwanted behaviors, especially so this prompting might affect disproportionately to profiles that do not follow stereotypes. So the question is how to implement the appropriate user intervention without negative effect. Before I conclude, I wanted to quickly mention a recent study in a separate study that will look at user intervention in general. So in this study, we tried to figure out whether explaining why a fake photo is a fake can help. Essentially, we show people manipulated photos and explain to them how this photo has been manipulated and to see how that impact users' perception, right? So in this particular example, as you can see, the original image pictured 6 Democratic lawmakers in the US. They are also called the Squad. And in the manipulated images, which is kind of collected from the internet, this is someone manipulated the photo and spread it out, and this went viral. Is that the image has been their clothes has been changed to colors, and Nazi symbols has been added to their clothes and their masks. So they try to push the narrative that these lawmakers have extreme views. So we try to say if explaining the manipulation and highlights the manipulated areas would help users to, change their perception. So what we found as the initial results is that explanation did help to make participants less agreeing with the intended messages behind the manipulation. But surprisingly, the explanation also has a negative effect on the feelings or sentiments towards the people or subjects in the image. So people tend to feel more negative when you're highlighting those manipulations, and they kind of project the negative feelings to the subjects in the image. So basically, the takeaway is that intervention is hard. So we're still trying to figure out the proper way to communicate with users on those manipulation attempts. All right, so in conclusion, so what we want to say here is that there is a need to robustify our tools to detect and analyze online deception and cybercrimes in general. So in this talk, I only show an example of perceptual hashing, but in many of our tools fall into this category, such as stylometry analysis, clickstream analysis, digital fingerprinting, that uses statistical methods to make inferences. So we need a more principled way to make them reliable. So another takeaway is that individual users alone seems to be insufficient to act as a defense against those artifacts, fake content. But there might be a hope for human and algorithm to work together on this end. So humans are in general are good at making reasoning based on information from different sources, but they might not be able to detect the subtle artifacts in some of those content. And machine learning can do well on those ends to do very specific tasks if you just train the algorithm to look for certain artifacts. There's an opportunity to combine their strengths to make the defense more reliable. And finally, we do believe that the more measurements are needed. So as we can see, some anecdotes that deepfake are increasingly used to create those content. It will be interesting to further study how prevalent they are in real world and how they were adapting as the defenses are ramping up. So it's important to identify any potential gaps between our threat models and the attacker behaviors in the real world to make sure we're solving the right problem. So with that, I want to thank you for attending the talk. I'm happy to take questions now. Thank you.
Thank you, Wang. So, and this is the little round of applause with the Zoom icon, but we'll soon resume that feeling of having an audience and having a real round of applause. So thank you very much. It was absolutely fascinating, and let me just stop the recording and the live stream as well afterwards.